The lenses used in optical instruments, such as eyeglasses, cameras, and telescopes, are made from transparent materials that refract light. They refract light in such a way that an image of the source of the light is formed. Here we show a crude lens formed from two glass prisms. Suppose that an object centered on the principal axis is infinitely far from the lens, so the rays from the object are parallel to the principal axis. In passing through the prisms, these rays are bent toward the axis because of refraction. Unfortunately, the rays do not all cross the axis at the same place, and therefore, such a crude lens gives rise to, at best, a blurred image of the object. A better lens can be constructed from a single piece of transparent material with properly curved surfaces, often spherical, as shown here. With this improved lens, rays that are near the principal axis, called paraxial rays, and parallel to it, converge to a single point on the axis after emerging from the lens. This point is called the focal point F of the lens. Thus, an object located infinitely far away on the principal axis leads to an image at the focal point of the lens. The distance between the focal point and the lens is called the focal length, F. In what follows, we assume the lens is so thin compared to the focal length F that it makes no difference whether F is measured between the focal point and either surface of the lens or the center of the lens. The type of lens shown here is a converging lens because it causes incident parallel rays to converge at the focal point. Another type of lens found in optical instruments is a diverging lens, which causes incident parallel rays to diverge after exiting the lens. Two prisms can also be used to form a crude diverging lens, as seen here. In a properly designed diverging lens, shown here, paraxial rays that are parallel to the principal axis appear to originate from a single point on the axis after passing through the lens. This point is the focal point F, and its distance F from the lens is the focal length. Again, we assume that the lens is thin compared to the focal length. Converging and diverging lenses come in a variety of shapes, as we show here. Observe that the converging lenses are thicker in the middle than on the outer edges, and diverging lenses are thicker at the edges than in the middle. The different lens shapes have advantages under certain conditions or particular applications. However, our future discussions on lenses and the equations that describe their properties only depend on the lenses being either converging or diverging.